All right, we're going to look at curve sketching for this this function here. Again, in the book they say y equals x to the 5/3 minus 5x to the 2/3. I like the notation abilities you get when you use function notation, f of x, so I'm going to do that. Call it f of x here. And the first thing I want to do is just think about f of x here. What do we know about it? And the rational exponents there, the 3 in the denominator for each of them, is a cube root. And so the first thing you want to think about is maybe the domain of the function. And when the only root occurring here is a cube root, that doesn't really limit the domain. There's also no other function type in this function that's limiting the domain. So our domain is going to be all real numbers. Know that right away. You might choose to factor this. It's not a bad idea. It helps you to find things like zeros. So if I factor out a common factor, x to the 2/3, that's going to leave from that first term, if I factor out an x to the 2/3, it leaves an x to the 1. Whoops. Because 2/3 times 1, I'm sorry, x to the 2/3 times x to the 1 is x to the 5/3, right? You add the exponents. So x minus 5, and the zeros of this function is another thing we can find here. X to the 2/3 gives us a 0 of 0, right? And x minus 5 gives us a 0 at 5. So zeros, x equals 0, x equals 5. So those will be x-intercepts on our graph. And actually 0, 0 is going to be a y-intercept also. So far, so good. End behavior. Let's take the limit as x approaches infinity and also negative infinity of this function. And when you look at this, I'll just say f of x, I kind of think maybe the factored form is easier. It doesn't really matter though. If you look here though, you can see that both of those factors, the x to the 2/3 is going to approach infinity as x approaches infinity, and so is the x minus 5. And so because of that, that limit as x approaches infinity is just going to be infinity. And as x approaches negative infinity, well, when you plug a large value of x in, that negative 2/3 power, the even power on top is going to make it positive, right? And then when you cube root it, it's still positive. Or if you cube root it first, it's negative, but then when you square it, it's going to be positive. So that factor will come out positive when you plug in a large negative value. However, the x minus 5 will definitely be negative. So, when you multiply positive times a negative, you get a negative. Makes it clear enough. If you want to look at it over here instead, this term will be positive, but then, with a negative in front of it, it'll also come out negative. And then, of course, the x to the 5/3 with odds on top and bottom, and that exponent will be negative. All right, so either way, the limit as x approaches negative infinity, negative infinity. So we know which direction this thing is kind of moving in as we go out to either end. All right. It's a good start. Now let's talk about first derivative here. So f prime of x. Now when I'm doing the first derivative, I can go from any form of the original function that I like, and there's one I prefer here. I don't want to start from the factored form because then I have to do the product rule. Instead, I'm going to use that original form. So even though I did some work to it to factor it, that doesn't mean that's the easiest place to take the derivative from. Right? I like the original kind of expanded form better for derivatives. I can just do the power rule. So my derivative is going to be 5/3 x to the 2/3 minus, and then using the power rule again, 5 times 2/3 is 10/3 x to the negative 1/3. And then I'm going to factor this. I'd rather do the algebra after doing that derivative from the easier format. And so to factor, I'm going to take out, I'll take out a 5/3. Right? I definitely want to take out the 1/3 and kind of get the fraction on the outside. That's nice. And then I can also take out a 5 because 5 and 10. And then I'm also going to take out an x to the negative 1/3. When I have a common factor, even with these rational exponents, x and x on both of them, I like to take out the one with the lesser power, in this case the negative 1/3 power. That way, what's left once you take it out is going to have positive exponents inside, or non-negative exponents at least, inside of this set of parentheses. So when you're factoring out x to the negative 1/3, that means we're dividing it out. And when you divide like bases, you subtract the exponent. So 2/3 minus negative 1/3 is going to be positive 1. In other words, 2/3 is 1 more than negative 1/3, right? So that's going to leave an x to the first power at the beginning of this. And you can double check that if you're not sure about this factoring out a negative rational exponent like that. If you just kind of distribute it back in, 5/3 x to the negative 1/3 times x to the 1, you add the exponents. Yeah, that's going to give you 5/3 x to the 2/3. Good? Okay. And then from the second term there, we're going to have a negative, of course, and then a 2 because of the 10/3 as opposed to the 5/3, but the x to the negative 1/3 is the same, so that part's okay. And that's factored form's nice. We see that we have a place where that derivative, that first derivative, does not exist at x equals 0 because of the negative power there. I'm just going to tighten this up a little, that -2. And in fact, you could rewrite this if you want as 5x minus 2 on top over 3x to the 1/3, right? Or better yet, 3 times the cube root of x. So this x to the negative 1/3 puts it in the denominator because of that negative power. So at x equals 0, that means it's undefined. So f prime has a 0 denominator. It does not exist at x equals 0. That's good to know. Keep in mind, that is in the domain, right? Our domain for this function was all real numbers. So that means what it's actually going to be, since the derivative has a 0 denominator there, that means we're going to have a vertical tangent there. And in this case, I believe it's going to be a cusp where it kind of comes into a point, a sharp point from either side. But we'll see that in our sign chart in a minute. And then if you look at the zeros on top there, f prime equals 0 at x equals 2. So that's going to be a horizontal tangent, right, when the derivative equals 0. Okay, I should, when I said vertical tangent here, I mentioned I believe it's a cusp. Actually, I'm not sure yet. We'll see in the sign chart. It's a vertical tangent, though. It could, if it's a cusp, then it's going to be a vertical tangent from either side. The nomenclature might be a little funky there, though, because, do you call it a vertical tangent if you have that sharp directional change? Let's see what happens, though. I'll say possible cusp. But it's also possible, and we can tell if we look back at the original function, but we'll see it in the sign chart. It's also possible to get a vertical tangent like that when you get a case like this where a first derivative does not exist. But let's look at the evidence in our sign chart for f prime. Okay, and we can do that pretty quickly here. The domain's all real numbers, so I want my kind of number line here for this sign chart to go in both directions toward the infinities. And my key numbers are just 0 and 2, right? The zeros of the numerator and denominator here. So 0 and 2. And if you want to split up factors, you can do like x minus 2 factor and say that's negative until you get to 2, and then it's positive. And then the cube root of x to the 1/3 factor, which is going to be negative until 0, and then it's going to be positive. Of course, the 5/3 is just a constant multiple and it's positive. You could throw it on either one of these or just leave it off. It's not going to affect the sign. Anyway, 2 negatives make a positive. This makes a negative, that's a positive. And so we do have a sign change in the derivative at both 0 and at 2, which means that they are both relative extrema, right? They're both values in the domain of the original function, so they are points on the graph, and both of them have the sign change in the derivative. So we're going to get a relative maximum at 0 and a relative minimum at 2 because of the way that f prime changes signs there. In fact, let me say that. F has a relative max at x equals 0. And again, this is the one where we had the vertical tangent, and it is going to be a cusp. That's what that means, right? If we have a maximum there and the tangent line is approaching a slope of infinity from each side, that zero denominator in the derivative, that means that you have a cusp. So let me write that, a cusp. But it's still a relative maximum. It's still a point on the graph. It's still the highest point in its neighborhood. And a relative min at x equals 2. And if I was writing this on the AP exam, I would justify these answers. I would say f has a relative max at x equals 0 because f prime changes signs from positive to negative there. And f has a relative min at x equals 2 because f prime changes from negative to positive there. Meanwhile, I'm actually